Hi students, I'd like to briefly introduce what was covered in the last lecture. So in the previous lecture, you have learned a node with a doubly linked list, previous and next, okay, previous, next. But you can just generalize this, just make them as additional row, which is left and right. Okay, and the left and right are the just children. So your single node has two additional links for the left child, for the right child. In that case, you can make it as a binary tree. Or if you want to ternary tree, you need 3 additional pointers for the children. Okay. So, but the binary tree is a very convenient one because it may represent various concepts in computing problems. So it is very famous. So you have to be aware, of it, and you have to be familiar with the operations of a binary tree. So today we'd like to exercise it with a simple problem. The problem is named Infix to Postfix. So let me switch the screen to your laboratory handout. So while it is opening, I'd like to explain what is a postfix and what is infix of an expression. So the postfix and infix notation of an expression is paraphrased, can be paraphrased from the structure of the expression tree. So once you are considering the expression tree, then you may understand what is prefix and what is the postfix. Okay. Can you see this laboratory handout? Okay, good. So in the laboratory handout, it is saying that postfix to infix translator. So before that, you have to be familiar with the expression tree. An expression with a binary operator can be represented as a binary tree. So I just implemented a simple binary tree here. But before that, I'd like to just draw the expression tree for 1 plus 2 times 3. Okay. So as you know, the 2 times operator has a higher precedence than the addition. So the addition should be performed later than the multiplication. And the left operand is 1. And the left operand of the multiplication is 2. And the right operand is 3. And the right operand of plus is the result of 2 times 3. But you do not evaluate it, okay? Just represent it as a tree. So simply you can write this, but with the specific links, you can write this as plus here, okay? And the left link is for 1, which is a leaf node, and 2 additional links are known, null pointers. And for the right subtree, it is the multiplication. multiplication here. And then you can make that the similar two nodes, which is representing 2 and 3 respectively. Okay, so you're understanding this structure, right? Should I explain this again? So here here I need some audience. Okay, so thank you, Sumin. Okay, so I'd like to erase all the drawing and just take a look of this code. This code is just a filled up code of the skeleton of your lecture note. So you are implementing a class, two classes. One is a tree node, the other is a binary tree. Okay, so you have two classes, and the binary tree is a friend of a tree node. So that means all the methods in the binary tree can access the private fields, which is data, left child, right child, and so forth. And it has a public constructor accepting a string. So in this simple example, you do not regard 1 or 2 as numbers. They are treated as a string. And to left subtree and right subtree nodes can be accepted, but you know that this is for representing a default argument. Okay, that means a tree node constructor is conceptually overloaded. It can accept a single parameter, which is a string, but it can accept two parameters, string and left child, and it can accept three parameters, string, which is the data, and left child pointer and the right child pointer. Okay, and all the fields are initializing the private fields. Okay, it is so simple. For binary tree, it is further simpler than the tree nodes. It is accepting a tree node pointer, and it is initializing the root of a binary tree. Okay, so there's no default constructor of the binary tree. You have to supply at least one tree node. Okay, and this print routine is for printing a tree. So it is accepting indent as additional default argument. So in default, it is set as 0. But without it, it is applied with a certain value, which is indented from the left. For example, for the source code itself here is 4 spaces are indented here. So you are generating an indent string by repeating indent, repeating space for the indent number of times. So if indent is 4, then this string is constructed with 4 repeat of the spaces. So this kind of string will be generated. Okay, and it is examining the root. If it is not null, so this has the same meaning that root is not null pointer. Okay, so if it is not null, you'd like to print the indent string and print the root data and end the line. So simple. Okay, but this is somewhat complex part because it is calling a recursion calling itself, okay? But before that, you have to aware that tree node is not a binary tree. So you have to make a binary tree for the left subtree and the right subtree. And those binary trees are printed out with a +4 indentation, okay? Any questions on this code? No questions? Okay, good. Then I'd like to make it a little bit, okay, for the main code. It is creating a tree node 2, 3. So this can be depicted for the previous cases. Okay, so you are making a node 2. That means both links are empty, are null. Okay, so this is left node. So you are creating another node 3, and both children are null pointers. So this is R node. Okay, and you are making a multiplication with left with L node is pointed here, R node is pointed here, and itself is changed as R node. Okay, and you're making a new node which is 1, and you know that for the default argument, using the default argument, both of them is null, and it is set as left node here. Okay, so you're making a new plus node, and the left node is pointed by left node here, and the right node is pointed by here. Okay, and you set it as a root. Okay, so you're assigning root here. But the root is, the type of a root node is tree node, not a binary tree. So you are constructing it a T whose T type is binary tree. Okay, so for the binary tree, you can print it to see out. Okay, so the two types interoperation to make a binary tree. Any questions up to here? No questions? Then let me show this from your Visual Studio Code. So in your Visual Studio Code, okay, so let me just resharing my Visual Studio Code here. Okay, so it is set as a tree node. A friend class is a binary tree, and left child, right child. So those are already explained, okay? And you just put it, once you are installing run code, then you can press this to build and execute the code. Okay, it is done +1 times 2, 3. So you can make a tree. You can depict a tree simply as in the first diagram, +1 times 2, 3. So let's traverse this as infix notation. That means infix of a tree here. So let's think about this is tree. That means infix of tree that left child plus tree that root plus infix of tree that right child. Okay, so what is the infix of this tree? Infix, you have to evaluate infix tree that left child, which is 1. Okay, and root is plus. Right child is for infix. You have to evaluate the infix of the left first, 2. And the root of this subtree is times. Okay, and root the right child, infix of the right child is 3. Okay, so how about the postfix? It is similar to infix, but okay, let's just save this or save this a little bit, and I'd like to erase some part of it. I have to erase the whole part of this. Okay, so this is infix, you know that, so removed. Okay, and the postfix of it, what was wrong? Okay, postfix of a tree is the postfix of tree left child and postfix of the right child and tree that root. Since it is, you know that root comes after traversing the subtrees, so it is called a postfix. You know that post means afterwards. So how to make a postfix? You have to make a postfix of this 1. You have to make a postfix of this right subtree. Okay, so for that you have to generate the postfix of the left subtree, which is 2. Shao, can you see the pen direction? Yeah. Okay, so 2, and the postfix of the right subtree is 3, and the root is of the subtree is times. Afterwards, you know that this is the postfix of right subtree, and then plus comes here. Okay. So you are assuming that this kind of postfix is given to you, and you are reconstructing the expression tree, and then generate an infix notation. Okay, so that is the goal of today's problem. So let me, do you have any questions up here? Questions? Then let me reshare the handout. So this simple paragraph is saying that if you want to remove the temporary tree, which means that left tree and right tree here, then you can make a tree node as an internal nested class into here. Then you can make this one and this one as a binary tree. Okay, rather than making a tree node. So your code can be further simplified, but with additional sacrificing with additional complexity for the nested classes. In that case, making tree node into the binary tree can be much convenient, okay? So the programming laboratory 9 is post to infix the CPP, assuming that the post-order traversal of an expression tree is given, generate the in-order traversal of the corresponding expression tree. But there is one limitation. I'll explain that. It is convenient to build the binary tree first and then generate the in-order traversal. Constructing the expression tree, a stack of tree nodes, can be convenient, which means that, for example, you know that this is your postfix. Okay, this is your postfix. Then how to make the expression tree is that once you get the operand 1, know that you have seen the operand 1, then push 1 into a stack. So this is a stack of tree nodes. Okay, so you can make a tree node for 1 and push it. For the second case, for the number 2, so you can make a tree node 2. Okay, so if you want to be explicit, I erase this and more explicit way, make it more explicit way that we'll make a tree node of 1 with null here, and this is pointed by your stack. Okay, in that case, you have to make a tree node pointer stack. Okay, for 2, you can make 2 is pushed here. For 3, you can make 3 is node 3 is integer node 3 is made, and this is pushed here. And for the binary operator times, you just pop it. Pop this one. So you may save this as right child. Okay, this is popped. And how about popping this one? Because this is a binary expression. Save this as a left child. Okay, and then you make times node with the left child here, the right child here. And the result is pushed onto the stack. Okay, so you know that this is pushed. Why are the things erased? Okay, so in this way, you can also implement plus. Since it is a binary tree, you are popping this one as a right child. Okay, so you have to redirect this. No, that is not. Sorry. Okay, so let's make it correctly. Okay, so you know that this is a right child, and the right child is popped here, so this is a right child, and left child is popped here. This is your left child. Okay, so that means you have to erase this, erase this, erase this, erase this, and then make a plus node. Make a plus node. So let's make it here. Plus node with the left child is here and right child is here. And this is pushed onto your stack. Okay, so finally you have eaten all the, you have processed all the input, and your stack should contain a single tree node. Okay, so this is your tree representation. So it is described here. So the input is an operand, make a node and push it. If the input is an operator, pop two nodes from the stack and make a new tree node with the operator and the operands popped. Repeat the above steps until the input is empty. Executing the algorithm, you will get the expression tree from the stack top once the postal traversal is correct. So given the input string, for example, okay, so let me save this a little bit and erase all the drawing and switch it to the mouse. Okay, so push 1, push 2, push 3, pop 3, pop 2, which is right child, left child, and push 2 times 3. Okay, pop 2 times 3, pop 1, and push 1 plus 2 times 3. This is the right child and left child. Note the order of popped operands is just a reverse order of the operands in order. That means the right operand is popped before the left one. So your program should read. So do you have any questions up here? No questions? Okay.
Excuse
So
me,
your
Professor.
program should read from standard input. The first line of the input contains a positive integer n. The number of input items, which means that number of operators and operands in OR. And the second line contains n items separated by space, which is the postal traversal. An item can be either an integer operand or binary operator, one or plus, minus, times, and divide. So your program should print the result to the standard output, but your result should be in the traversal of the expression tree, but here is a restriction. Note that your inner traversal needs a pair of parentheses per operator. For example, you need a pair for the times here. You need a pair for the addition. So the inner traversal is parenthesized plus 1 plus opening parentheses 2 times 3, closing parentheses twice. Okay, so you may decipher this by yourself. Any questions?
Yes, Professor, I have a question.
Okay.
As you explained the problem,
Mm-hmm.
I don't understand why we should use tree. So only stack is needed to solve it. Why do we need to use binary tree?
Okay, that is a very good question. So I summarize the question of Ilya. So Ilya is saying that for the infix traverser, infix notation, you don't need actually make a tree. Okay, so you can make it on the fly rather than making a tree node. But you know that this is for exercising the binary tree. So at first, I was designed it for generating level order traversal. It is for more appropriate for making a tree. So you have a good reason to make a tree. But I just decided that may be too complex for some students. So I'd like to just relieve your burden in this simple exercise. So that is the reason. There is no other reasons. Okay. Do you understand, Obrotov?
Yes, thank you.
Thank you for your understanding. So any other questions? No questions? Then I'd like to explain the requirements of bonus points. Okay, so this is not just solving this truly, but I'd like to just sketch the skeleton using your Visual Studio Code. So the bonus point is making that you want to move. So let's save this as save as, because that will expression tree 2. Okay. So the bonus point, for the bonus point, you want to move this into the class here. Okay. So the class tree node is nested into the binary tree. So you may want, if you want to make it public, then that means the class name is available for the outside. Okay. But for that, it is not. Okay. So for that, in that case, you have to make this X, because your root is needs a tree node type, and you need additional public visibility keyword here. Okay, so your tree node is a root, but you can make this as a binary tree rather than the tree node. Binary tree. Okay, so that may be more appropriate in some cases. Okay, so if you want to get a bonus point, you'd like to make a tree node in this style. Okay, so you are making a tree node inside of a binary tree, then maybe more encapsulated rather than the material introduced in your lecture note. Okay, so in that case, you have to modify the tree node constructor, and other things should be modified, modified also. Okay. Do you have any questions for the bonus points? No questions? Okay, good. Then you are about 35 minutes, 32 minutes to go. So thank you all for joining this lecture, and please try this because it is a very simple problem, and I hope all of you get full points today. Okay. So if you don't have any questions, do you have any questions?